Hello everyone, I'm Showkot Hossain presenting our research work titled Towards Blockchain-Driven Network Log Management System in 8th IEEE International Conference on Smart City and Informatization. It is a brief overview of our presentation. We will discuss the following key points of our work one by one. We know that log data plays an essential role in ensuring the security of a network. Usually, different entities of IT infrastructure such as servers, firewalls, routers, switches, individual PCs generate log records. These log records provide us essential information to identify and troubleshoot different improper activities affecting to the network. While this log data can help us in various ways, log data can itself be tampered to prevent the detection of system compromises and hide malicious activities. So the big question is how to maintain the integrity of huge volume of log data. The traditional log management system usually use the state-of-the-art storage devices and cloud to store the abundant log files. They are subject to a single point of failure and also lack transparency and trust, as the users have no control over the stored data. It is possible that an internal or external adversary tampered the log record. Security and privacy of network log data is an active area of research. Olaf and Esmeralda proposed a mechanism where a centralized server located on a secured place connected to the network environment collects log events. This scheme is vulnerable to a single point of failure and also lacks an efficient query mechanism. Indrajit and others presented a solution to store log records in a server running in a cloud-based environment. As the cloud is semi-trusted, there is no guarantee on the consistency of data and illegal access. Moreover, the cloud server is a single point of failure. Blockchain is used in literature to store and perform cloud forensics. Liang and others proposed a blockchain-based architecture known as ProofChain to collect and verify log data provenance by associating provenance data to blockchain transactions. When a user operates on files stored on the cloud, a corresponding provenance entry is generated and stored locally in the provenance database and uploaded to the blockchain network by the cloud service provider. The user can request a provenance auditor to validate data stored in the provenance database. And William and other proposed LogChain, a blockchain-based immutable log storage for cloud service providers. The proposed scheme converts blockchain to a circular one to form a hierarchical ledger to overcome the scalability issues. The authors has implemented a prototype known as LogChain as a service that needs more enhancement for production implementation, and the API of LCAS has not been implemented yet. However, existing works cannot guarantee log data confidentiality, lack efficient query mechanism, real-time implementation, and performance analysis of blockchain-based log management schemes. To solve the existing problems discussed earlier, we propose and implement a blockchain-based network log management system that can efficiently store, query, and audit log records while preserving the confidentiality of log records. Our scheme eliminates the single point of failure and ensures data immutability, data accountability, and transparency with low computational overhead. Here is the system model of our proposed scheme. Our system consists of mainly three entities: the blockchain network, participant nodes, and a local database. Blockchain network is a decentralized peer-to-peer network that stores data in an immutable way. Once data is published in blockchain, it is quite impossible to change or remove the data. Participant nodes are the end users of our proposed system, and there are four types of participant nodes. Admin nodes are the super users exercising almost every control over the blockchain. Miner nodes are a set of nodes chosen by the administrators who can mine the blocks and cryptographically seal them. User nodes periodically publish the log data to their from their machine to blockchain network. Auditor nodes are responsible for auditing the transactions to detect illegal changes in the local machines by internal or external adversaries. When they detect any discrepancy in the log record, they notify the owner of the data. Finally, local databases stores log data in private cloud of an organization, and it is shared among the employees and auditors in our schemes. Auditors use the read-only log files to conduct audit operations. Now, I will present the main features of our proposed scheme. These are the components of our proposed system that have been already discussed in previous slide. We propose an admin node selection algorithm where each of the current admin nodes execute the algorithm after a predefined time interval to reach a consensus. There are at most n times p number of nodes with admin permission, where n is the total number of nodes in blockchain network and p can be any value between 0 and 1. Since the algorithm periodically changes the current admins of the system cannot be manipulated by any individual admin. Data published to the blockchain network are visible to every node in the network by default, which is actually loss of confidentiality. We use advanced encryption standard AES to encrypt and decrypt data. In our approach, each node generates a RSA key pair, saves it to a SQL location, and then publishes the corresponding RSA public key to the blockchain network. A node who wants log data confidentiality generates AES key, encrypts the log data using that key, and then publishes the encrypted data to the blockchain. Whenever it wants a node to see its data, it shares the AES encryption key through the blockchain by encrypting it with the intended recipient's RSA public key. After that, the recipient can retrieve the encrypted AES key from the blockchain, decrypt it using his RSA private key, and use the key for decrypting the log records. Hence, the confidentiality is preserved. Our proposed scheme handles both encrypted and plain text log records. To perform query operation on both types of data, we implement an integrated mechanism using multisig. It uses keys associated with a log record to support various query operations. In our scheme, log records are searched in two levels. The first level search is performed on blockchain, which we denote the single phase query. One thing to note that only the timestamp associated with log records is used as a key during the publishing log records to the blockchain. Therefore, in a single phase query, we can only search on a timestamp key or provide a range of timestamp to perform search operations. In the two-phase query, we perform queries on log records fetched during single phase query. However, this query is performed at the application level. We can search on a single key or multiple key in this phase. We can also perform AND or operation on the result of multiple key search. The table lists the queries we have defined along with their complexity for plain text logs. For instance, the complexity of a multiple key AND query is big O of log n plus big O of MP, where n is the number of items retrieved from the blockchain with those keys, m is the average length of log records, and p is the number of records retrieved in a single phase query. The complexity for the encrypted log records will be same as the plain text except the fact that an additional time d is required for decrypting the log records. As transactions already published in the blockchain network are immutable, blockchain provides an exact copy of the log records. Auditors have access permission to the blockchain and they can detect any types of data inconsistency in the network log by matching the data stored in the local database and the log records stored in the blockchain. To audit, the users specify range of dates and the auditor nodes retrieve all the transactions between the specified range using a timestamp range query from blockchain. In the case of encrypted log records, auditor nodes need to decrypt the log records. In a scheme, several auditors work in parallel, and a node accepts a decision if more than 51% auditors vote for that decision, similar to consensus algorithms in blockchain. To implement the proposed system, we used multi-chain to create the blockchain network, which is an open source private blockchain platform. We design a web interface to interact with the blockchain network easily. Python is our backend language, and Python Flux framework is used to implement the web application. Additionally, we use MCRPC library in Python to interact with the blockchain network via multi-chain JSON RPC. All the participant nodes of blockchain were run on PCs consisting of Ubuntu 18.04 as operating system, 8 GB of RAM, 1 terabyte of hard disk, and Intel Core i7 processor. We used syslog as the source of log records, which is a general standard to keep records of the system and program messages generated in the Linux environment. To evaluate the performance, we used 670 megabyte syslog data collected from a laboratory consisting of 35 uh, personal computers of our institution. We measured several metrics to evaluate the performance of our system. The primary performance metric was the processing time, which we considered as the time to extract and encrypt log records, publish and retrieve records, query processing time, and block mining time. Our results were averaged over 50 samples. Here, in this figure, you can see the record extraction and encryption overhead. Record extraction time is the total time to search and retrieve records from a log file belonging to a given time interval. And the encryption time is the time to encrypt the extracted log using AES 256 encryption. As shown in the figure, time to extract records from a log files increases almost linearly with the increasing size of chunk. A slight deviation is observed in the graph due to the placement of chunks in the log files. After extracting and encrypting, log records will be published to blockchain and they will be retrieved from the blockchain as the need arises for query and auditing the log records. As we can see from the figure, both publish and retrieve time increases linearly with chunk size. We have already discussed the query mechanism. We have derived associated time complexity for those queries. To evaluate the query operation in our experiment, we measure the query time for both or and against the number of keys and number of records, respectively. Here, The query processing includes retrieval time of log records, decryption time if necessary, and search time on the retrieved data. From figure A, we can see that the query processing time for the multiple key and query is unchanged to the increasing number of keys, whereas for the multiple key or query, it increases with the increasing number of keys. From figure B, we can see that query time for both the OR and AND query increases linearly with the number of records. Another thing to notice from the graph is that the number of query time for encrypted log record is higher than the plain text logs, as it includes an additional decryption time. In this experiment, we try to measure how the interval between successive blocks differed from the target block time parameter of blockchain. We performed 100 transactions, each with a payload of 1 megabyte, and traced the transactions were mined into 14 different blocks. From the given table, we see that 12 blocks contain 9 transactions, and the other two have 3 transactions each. We can also see that the average time difference between two successive blocks is very close to 15 seconds, which is the value of target block time parameter of blockchain. In this paper, we have proposed a blockchain-based framework that can store log records efficiently and perform query and audit operations on the stored log records. Our scheme achieves data immutability, transparency, and data accountability through the use of blockchain. It ensures privacy of log records and provides a realistic log management system compared to the current work in the literacy. We aim to make the proposed scheme more practical by making the system more scalable using the off-chain mechanism to store log data outside the blockchain and incorporate attack probability of the network. Here are the list of references we have used in our paper. Thank you all for listening to the presentation. And obviously, feel free to reach us if you have any questions regarding our work. We will be happy to answer your query. Thank you all. Have a good day.